Hey guys, in this video we're going to talk about Chapter 14, Section 1, the partial derivative. So we have finally gotten to the calculus in Calculus 3. So let's go ahead and recall a definition from Calculus 1. So in the very beginning of Calculus 1, we talked about limits, and specifically we talked about the limit definition of a derivative, right? And so this right here was our limit definition of a derivative. So f prime of x is what we call the derivative. And, in more familiar terminology, the derivative is just a function that tells us the slope of the tangent line to a point on the curve. So let's just remind ourselves how we dealt with derivatives in 2 dimensions, okay? And then we're going to extend that idea to 3-dimensional space. Okay. So how did we find the derivative of a function y equals x squared? Okay, so the first way that we did this, the first thing you learned is the limit definition of a derivative, and then we looked at the shortcut, right? So the shortcut, remember, was just the power rule. So the power rule said that we take our function, y equals x squared, and what we're going to do is we're going to multiply this exponent by the front number here and then subtract the exponent by 1 to get our derivative. So the shortcut tells us that f prime of x is just going to be 2 times the 1 in the front, right? So that's just 2. X, and then 2 minus 1 was just 1. So this is, our derivative is just going to be 2x to the 1, or 2x. Okay, so this was the derivative. And the derivative, again, it's a function, right? It depends on x, right? Because we have this function, y equals x squared. It looks something like this. It's our parabola right here. And the slope of the tangent line right here is going to be different from the slope of the tangent line, say, right here. It all depends on what your x value is. That's why the derivative is a function. It depends on x. It's not going to be, the same slope throughout unless you have a linear function. But anyway, so that's the derivative, and it says what is the slope of the tangent line at x equals negative 2? So the slope at x equals negative 2 is just going to be, we plug in negative 2 into our derivative function, right? We want to see what the slope is at x is negative 2. So we do 2 times negative 2, and that's going to give us negative 4. So that is the slope at x equals negative 2. And we can kind of see that on this little rough sketch right here. So if this is x is negative 2, we can see that we're sloping downward here. On the other hand, if we were to pick something like x is positive 2, we would see that when we plug in positive 2 into the derivative function, we get a slope of 4. We get a positive slope, and we can see that with our picture right here, that our tangent line is sloping upward. So that's how we did this with the shortcut. We also had the limit definition, which I want to bring back up. I know that you guys don't like it, but we are going to talk about the limit definition in 3 dimensions, so let's remind ourselves how to use it in 2 dimensions. So the limit definition says this. It says that f prime of x, the derivative of a function f of x, is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So in our case, we started with the function x squared. All right, so maybe I should actually label this f of x equals x squared. So this first piece, f of x plus h, I'm simply plugging in x plus h into my function. So f of x plus h is going to be x plus h squared, right? And I'm just plugging in x plus h as my input this time into the function x squared. Okay, and then we can go ahead and make that substitution here. We have the limit as h goes to 0 of f of x plus h, we just said was x plus h squared, minus f of x, we said that original function was x squared, all over h. And then we can simplify this guy, right? So x plus h, if I use the distributive property to FOIL it out, I get x squared plus xh plus xh plus h squared. So that's x squared plus 2xh plus h squared. All right, so let's rewrite that. Limit as h goes to 0. X plus h squared we just found was x squared plus 2xh plus h squared, and then we have that minus x squared still on top, all over h. Okay, these x squareds can cancel, and at this point, I have the limit as h goes to 0 of 2xh plus h squared over h, and notice on top I can factor out an h. So when I factor out an h on top, I'm left with h times 2x plus h all over h. These guys cancel, and I'm left with the limit as h goes to 0 of 2x plus h. So I just plug in 0 for h. Since I have a polynomial, I can do that with limits. And so this is just going to be 2x plus 0, which is 2x. And therefore, my derivative is 2x. That's how we found it with the limit definition. And that corresponds with what we got up here with the shortcut, with the power rule. So we know what tangent lines to curves look like in 2 dimensions, right? So we had something like this. So y equals x squared, and we could easily figure out what the tangent line to any point on this curve would be, right? There's only one tangent line for each point on the curve. But what if we have a surface in 3 dimensions? So if I give you a point right here, say P, and I ask you for a tangent line to that point, like you're imagining holding this bowl in your hand, right? And I'm asking you for a tangent line to that point. Well, you could have several tangent lines, right? You could have a tangent line that only touches the bowl at this point, right? You could have a tangent line that only touches the bowl at this point. You could have a tangent line that only touches the bowl at this point. So there's an issue here, right? We don't have a well-defined tangent line to a 3D surface, whereas in the 2D case, right, when we were working in a 2-dimensional space, we could define a tangent line to a point only in one way. So that's going to cause a little bit of an issue. So which tangent line do I mean in the 3D case? So what we're going to do, the idea is that we're going to restrict our directions so that we know exactly which tangent line we want, right? Because again, in this case right here, there are infinitely many tangent lines that you can draw to that point P, right? That's only going to touch that bowl at P. But we want to specify which tangent line do I want to choose, right? Which tangent line do I want to find the slope of? And to do that, we need to restrict our directions so we can find the slope of the tangent line, aka the derivative. We're going to start by looking at the slope in the x direction and the y direction, and then later on we're going to talk about directions more generally. Okay? So I'm going to just explain what we're going to do, and then hopefully I can show you visually what I'm trying to explain here. Okay, so when looking in the x direction, when we are trying to find the slope in the x direction, we want to consider the slope of the surface when y is constant, when it's just a number. And so what we're going to do is we're going to look at planes parallel to the xz plane. Remember, in the very beginning of this course, we saw that the xz plane consisted of y could be anything, basically, with the xz plane. So y was just a constant number. On the other hand, when we look in the y direction, we're going to consider the slope of the surface when x is fixed, or x is constant. And so we're going to be looking at planes parallel to the yz plane. Okay, so let's just take a look at a concrete example, and I'm going to put this in GeoGebra as well. We're trying to figure out, first of all, what is the derivative of this surface, z equals x squared plus y squared, at the point x equals 1, y equals negative 2, and z equals 5, and we want to consider the slope in the x direction, okay? So this is what we're going to do, all right? So I have our surface plotted in GeoGebra here. It's a bowl, right? And I also have our point A is 1, -2, 5 plotted. And then I have two planes. Okay, the first plane is when x is fixed, that's pink, and the second plane is when y is fixed, that's blue. Okay, so let's take a look at what's happening here. So in the x direction, when I look at the slope in the x direction, I'm fixing y. So I'm considering fixing y. I'm looking at a plane that is parallel to the xz plane. Okay, so I'm looking at a plane that is parallel to the xz plane. So notice that when I have my figure, pointing in this direction, we can see the x-plane, we can see the x-axis in red, we can see the z-axis in blue, so that's the xz plane, and if I shift this picture a little bit, we can see that the blue plane is indeed parallel to the xz plane, okay? Ignoring the pink plane for now. And so, when I look at it this way, I see my point on the parabola, right? I see my point on that cross section, that A point, and I'm trying to figure out what the slope of the tangent line at that point is. And I can do this now because I'm looking at this in a two-dimensional sense, right? I'm looking at, instead of the y-axis, like we would look at in Calc 1, this time we're looking at the z-axis, right? And we're looking at the z-axis and the x-axis together, just like we would look at the y and the x-axis together in Calc 1. So the idea here is, okay, look at this curve, all right? So this cross section right here, this plane is intersecting our surface in a parabola, right? And that point is going to have a tangent line. It's going to have some slope associated with it, right? And that slope is going to be positive. You can imagine drawing a line tangent to that point that I've plotted and seeing that the slope is positive. So this is the x direction. It's contained in a plane that is parallel to the xz plane, right? That blue plane is parallel to the xz plane. So that's the x direction, positive slope to the point A. Now, if I shift my view a little bit, if I shift my view to a plane that is parallel to the yz plane, okay, let me shift my view. Let me shift my view a little bit. Okay, so now I'm shifting my view. So the pink plane is parallel to the YZ plane, right? You can see the y-axis in green horizontally, and you can see the z-axis in blue. That's the vertical axis. And you can see our point A, the same point that we had before, but now we're looking at it from a different angle. Now, if you draw a tangent line to that point, the slope is going to be negative, right? So we have two different slopes associated with the same exact point on the bowl, all right? And that's the idea here with these, we call them partial derivatives, all right? So we say partial derivative of x, partial derivative with respect to y. And so that's the idea. The slope here is positive, right? The slope of that point is positive. The slope of the same exact point, but looking in this direction, is negative, all right? So let's go ahead and look at this algebraically. Okay, so what we're going to do to find the derivative in the x direction is we're going to fix y, right? And y is given to be -2. So if I plug in -2 for y, I'm fixing it, right? I'm saying, okay, -2 is y, and that's it. I'm not going to let y be anything else. So when I do that, I have x squared plus a -2 squared, and this becomes z equals x squared plus 4. So when I say, okay, y is only going to be -2, that is going to produce this cross-section x squared plus 4. Let's take a look at it again with the graph because I want you guys to really understand this concept. So when I'm fixing y equals -2, when I'm fixing y equals -2, I get this parabola. You can see where the point is on that parabola, and that parabola has an equation x squared plus 4, right? We said, okay, y is equal to -2. It's going to intersect that surface in a parabola, and that parabola is x squared plus 4 like we found, okay? So when I take the derivative of this, I'm going to call it f subscript x, okay? So that's the x derivative. You can think of it like that, partial derivative with respect to x. And we can use the shortcut to do that. So if I take, just like if this was y equals x squared plus 4, you would use the shortcut and say, well, okay, f prime of x is equal to 2x. Same thing here. If I take the derivative of x squared plus 4, the derivative is just going to be 2x. Okay, so what is the derivative in the x direction at that point? Well, I have to plug in the x value at that point. So my partial derivative at x is going to be 2 times 1, because that's our x value, and so that's 2. So again, let's go back to this picture. The slope of that line, tangent to A, is going to be 2. That's what this is saying, okay? Okay, so let's go to the y direction. Now with the y direction, we're holding x fixed. And what is x going to be fixed to be? Well, x is going to be 1 here. So if I hold x as 1, I have 1 squared plus y squared, and so this is just z equals y squared plus 1. So this is just a parabola in the yz plane, shifted up 1 unit. So this is my plane right here. This is z, this is y instead of x and y. And it's going to have the equation y squared plus 1. So that's, you know, if we shift views to this view right here, the parabola that this point lies on is going to be x squared plus 1. And you can kind of see at the bottom of that parabola, its vertex is at 1. Okay, and we expect the slope to be negative, right? We expect that slope to be negative. So if I figure out what the derivative of this is in the y direction, so this is f subscript y, partial derivative with respect to y, I just, use the shortcut but with respect to y, so this is going to be just 2y, and then I can plug in my actual y value here to get that slope. So this is going to be 2 times -2 is -4. So the partial derivative with respect to y is -4. The partial derivative with respect to x is 2. So the slope in the x direction is 2, while the slope in the y direction is -4. And we expected the slope to be negative, right, in this direction. But in this direction, we expect the slope to be positive. I hope this makes sense to you guys. I know it's kind of a lot to wrap your brain around at first, but it is really cool, and it's going to be really awesome when we start looking at derivatives in other directions, right? And this all has to do with parallel planes and what we've been talking about in the previous lectures. So let's go ahead and use the limit definition to take partial derivatives with respect to x and y, okay? So here is our definition. It looks very similar to the two-dimensional case. This is the partial derivative of f with respect to x at a point a comma b, okay? And notice what's happening here. Here, if we look at this f of a plus h comma b, we're holding the y value fixed, okay? So we're holding the y value fixed, right? And so let's go ahead and just use this definition to find the partial derivative with respect to x at 1, -2. So here, the point that we're interested is a equals 1, b equals -2. And so our f of xy is x squared plus y squared. So we have the following. We have the limit as h goes to 0. F of a plus h comma b. Okay, so that means we're plugging in a plus h for x, and we're plugging in -2 for y, right? So maybe I'll do this off to the side. So f of a plus h comma b, we're just plugging in a plus h in for x, so we have a plus h squared, plus we're plugging in negative 2 for y. Okay, so this is going to be, oh, and I should have actually plugged in the a is 1, so let me do that right here. This is 1 plus h squared plus negative 2 squared. So this is going to be 1 plus h times 1 plus h plus 4. So we have first, outer, inner, plus 2h plus h squared plus 4. So this is going to give us 5 plus 2h plus h squared. Okay, that's f of a plus h, comma b, right? Because a is 1, b is negative 2. Okay, so we have the limit as h goes to 0 of 5 plus 2h plus h squared, right, minus f of a comma b. Well, f of a comma b, we're just simply plugging in 1 for a and negative 2 for b into our function that we were given, our function with 2 inputs. Okay, so we have, this is going to be 1 squared plus negative 2 squared, so this is going to be 1 and 4 make 5. Okay, and this is all going to be over h. And so these 5s cancel out. I can factor out an h on top. So I have h on top, 2 plus h over h. Those h's cancel, plug in 0 for h to get our answer of 2, which is what we expected. This is the slope of the curve, or rather, this is the slope of the surface at the point 1 comma negative 2 in the x direction, okay? And that's exactly what we got right here. So, using the shortcut. Let's go ahead and use the same definition, but with respect to y. So this time, if you notice the difference between the two limit definitions, this time we're holding x fixed, or holding it constant. Okay, so we're gonna use this definition to figure out the derivative in the y direction. And what do we expect it to be? We expect it to be negative 4. That's what we expect our answer to be here. Okay, so the first thing is f of a plus b plus h. We have f of 1, and then b was negative 2. Again, we have a, b. We have 2 plus h minus f of 1 comma negative 2 all over h. We're taking the limit as h goes to 0. Okay, so if I plug in x is 1, y is negative 2 plus h into our function, I get 1 squared plus negative 2 plus h squared minus, and then f of 1 comma negative 2, well, that's going to be 1 squared plus negative 2 squared, and that's all over h, limit as h goes to 0. And let's simplify this guy. So we have limit as h goes to 0 of 1 plus, now negative 2 plus h squared is just negative 2 plus h times negative 2 plus h minus, and then in parentheses we have 5, so that's going to be minus 5 all over h. Okay, let's go ahead and FOIL this stuff out, clean it up a little bit. So we have 1 plus, and then when I FOIL, I get 4, negative 2h, negative 4h, plus h squared minus 5, all over h. And these 5s are going to cancel. So I have the limit as h goes to 0 of negative 4h plus h squared, so I can factor out an h, and I'm left with negative 4 plus h all over h. Those h's cancel, plug in 0 for h at this point, and we do indeed get negative 4. So that's going to be the slope of the tangent line in the y direction. It's negative 4. And that is exactly what we got right here. Okay? Okay, so this is a little section from your book, just visualizing partial derivatives on the graph. So this is kind of what we looked at with GeoGebra. This time they're looking at an upside down bowl. But essentially what you're doing is you're looking at the slope in different directions. You're looking at it from the x direction perspective, where we hold y constant. That's the partial derivative with respect to x. And then you can look at it in a different perspective, right? You can look at it from the perspective where you're holding x constant and you're looking in the y direction. And so, you can see just based on the perspective that you look at this, the slope's going to change. The slope here is positive. The slope here is negative. That's the whole idea here. So, we have infinitely many slopes that we can look at, but for now, we're just going to concentrate on two slopes, the x slope and the y slope, or the partial derivative with respect to x and the partial derivative with respect to y. Okay, so at each point labeled on the graph, determine whether the partial derivative is positive or negative. Okay, so remember that we're considering the x derivative and the y derivative. So the partial derivative in the x direction and the partial derivative in the y direction. So another way to think about these partial derivatives, so we have fx, this is the partial derivative with respect to x in the x direction. We can also think of it as the change in z over the change in x, right? This is our slope, but we're considering we're considering z to act like our dependent variable here and x as our independent variable. So for fy, this is the partial derivative, or f sub y, this is the partial derivative with respect to y. And we can think of this as the change in z over the change in y. So this is the slope in the y direction. And, maybe if you want to add a little subscript to help you remember that would work too. So let's first consider the point Q. Okay, so let's look at Q first. So for Q, for the partial derivative with respect to x, you want to ask yourself this. When x gets a little bigger, what happens to z? That's what you want to ask yourself. What happens to z when x just gets slightly bigger? Now remember, on this three-dimensional axis, this is positive x, right? Coming out of the page is positive x, whereas this guy in the back is negative, the negative x direction. For y, this is the positive y direction, and to the left is the negative y direction. So if we're at point Q and we just move a little bit in the x direction, let me actually maybe make this a little bit better. If we just move a little bit in the x direction, just a little bit, what happened to z? Did we move up or did we move down? Well, we moved down, right? We moved down just slightly, right? We moved down just slightly to get a smaller value of z right there. So when x gets a little bigger, what's happening to z? The answer is z gets a little smaller. Right? Because we moved a little bit down when we moved a little bit in the positive x direction. Okay? So is that going to correspond to a positive, a negative, or a zero slope? When z gets a little smaller, that's corresponding to a negative slope. Okay, so the partial derivative with respect to x is going to be negative around Q. Okay, so what about the partial with y? So what we're asking ourselves is, when y gets a little bigger, what happens to z? What happens to z. When y gets a little bigger, what happens to z? Okay, so now we consider when we move in the y direction just a little bit, right? Just a little bit. So when we move in the y direction just a little bit, it appears that our z is actually increasing a little bit. Okay, we're moving up on the object when y increases a bit. So we can say that our answer is z gets a little bigger, which would mean that we have a positive slope in the y direction. Okay, so that was Q. So this was all for point Q. Now let's take a look at what happens at point P. Okay, so at point P, we can do the same kind of analysis. So first with x, when x moves a little bit positive, right? If we start at P and we move a little bit in the positive x direction, what is happening to z? Are we moving up the object or are we moving down the object? Well, it looks like we're moving down the object, right? Because I started here at P and then I ended here, and that looks lower than where we started. So our answer here for P is f of x is negative, right? Because as x increases, z decreases, okay? What about the partial derivative with respect to y? Okay, and again, we're looking at point P. So when we move a little bit in the positive y direction, so if I go this way a little bit, what's happening to z? Well, again, I'm moving a little bit down from where I initially started. So this is going to be negative as well. Okay, so that is my answer there. Okay, so point A is shown on a contour diagram for a function with two inputs, x and y. So the first thing we want to do is evaluate f of a. And so all we're trying to do is to see what is our z value. And we can figure that out with the contour lines. So here we see that a is on a z value of 15, right? That's the contour lines tell us what z is for those points. And so our answer here is just going to be 15. F of a is 15. And so the next question says, is the partial derivative with respect to x of a positive, negative, or 0? So when x increases, what happens to z? That's what we're asking ourselves. What happens to z? Okay, so at A, if we move a little bit to the right in the x direction, right? If we move a little bit to the right, what's going to happen to z? Well, z is still going to be 15, right? We didn't move to the next contour line, right? So the answer is z stays the same. Z stays the same. And so the slope is going to be 0. Right, so that's what that means. When x increases and z stays the same, a slope is going to be 0. Okay. What about in the y direction? The partial derivative with respect to y of a is positive, negative, or 0. Well, what happens if we start at a and we go just a little bit up in the y direction? Right. So if we were to draw a contour line here, would that be bigger or smaller than 15? Well, it would be smaller, right? Because we can see that as we move up, the contour, the z values are getting smaller and smaller. So when z increases, when y increases, z decreases, right? So that means that our slope is going to be negative. Let's look at another example. And I encourage you guys to pause the video and see if you can do this one. Okay, so we have a point A on a contour diagram. We want to first evaluate f of a. So what is our z value when our inputs correspond to a? Well, we can see that that A is going to lie on the z equals 88 line. So that is our answer. F of A is 88. So is the partial derivative with respect to x near A positive, negative, or 0? Okay, so when x increases a little bit, what happens to z? When x increases a little bit, what happens to z? Well, if x increases just a little bit from A, are we going to be on a smaller z line? And the answer is yes, right? If we were to draw a contour line here, we would be somewhere between 88 and 82, noticing that the farther to the right I go, the smaller my z values are. So this is going to be negative. Okay. What about when y increases? So if we're at A and we increase y just a little bit, and we were to draw a line through here, well, again, that's going to be, that's going to be a decrease. We're going to be moving to a smaller z value. So this is also going to be negative. Okay. All right. Evaluate f of A. All right, we can see that A is on z equals 40. So that is our answer here, 40. Is the partial derivative with respect to x positive, negative, or 0? So if we start at A and we move a little bit to the right, if we increase x, what's happening to z? Well, z is going to be decreasing, right? Because we can see the trend here. As we move to the right, z is going to be decreasing. Z is getting smaller and smaller. So this is negative. Okay, what about the partial derivative with respect to y? If I go up just a little bit, and I were to draw a line here, would that have a smaller or bigger z value than the line where A was? Well, it's going to have a bigger one, right? Because we can see that as we move up, our z values are increasing. Okay, so this is positive. This is positive. Okay. Determine the sign of the partial derivative with respect to x and the partial derivative with respect to y at the point S using the contour diagram. Okay, so we're just doing the same thing. As x increases, what happens to z? As y increases, what happens to z? If z increases, that corresponds to positive. If z decreases, that corresponds to negative. And if z remains the same, it corresponds to 0. So here we are at S. So with f of x, we're looking to see what happens when x moves a little bit to the right. When x increases, we are on a new rung, right? And so we can see that, as we move in rings, the rings get smaller, right? We have z equals 18, z equals 16, z equals 14. So since we're going from an outer ring to a more inner ring, we're decreasing. So this is going to be negative. Okay. On the other hand, if we look at the partial derivative with respect to y, okay, so here we are at S. If we move up in the y direction, so if we move up, we're going to be at a more outer rung. So that's going to be positive, right? We're increasing the z as y increases. So this is positive. Okay, let's do one more. So we want to consider the contour diagram for the function f of xy, and we want to consider what's happening near point Q. Okay, so at point Q, which of the following is true? Partial derivative of x is positive, partial derivative with respect to y is positive. Is that true? Well, all we're doing is looking at what's happening around Q. So as x increases, we go to this rung, right, as x increases, and that is a decrease in z, right, because we went from z equals 7 to z equals 5. So this is not true. This is already negative right off the bat. We don't even have to verify if fy is positive. So that's not true. Neither is this one, because the partial derivative is not positive with respect to x. What about C? Okay, so this says partial derivative of, with respect to x is negative, partial derivative with respect to y is positive. Is that true? Well, let's look in the y direction. near Q. Okay, so if I increase my y value, if I go up, right, if I move up, I'm going up from z equals 7 to z equals 5, right? Again, I'm decreasing in z when I increase in y, so that's not true. F of y is negative, but also, partial derivative with respect to y is negative, partial derivative with respect to x is negative, so choice D is our answer right there.